Okay, hey, welcome to the Polymers lecture. One more after this that we'll talk about kind of sustainability and design, and I hope to get that out this week. It's a nasty week for me. My pattern seems to be Sunday night seems to be the one time I can get these things done. But hopefully you're enjoying these and getting something good out of this. Today's topic, and probably shouldn't go too long, I don't think, is going to be polymers and their structure, property, and processing. All very brief, obviously. In that we got 45 minutes or so to do this. And again, maybe this one won't go quite that long. Um, so anyway, a couple business things have come up on the discussion boards, and they're hard things to type out. Hopefully this works a little bit better. So at the end, I'm going to do a little phase diagram example that might pull things together, and maybe having seen some of that before and letting it seep will help. Um, Also, I'll do a little bit of a discussion on corrosion, and there was a problem in there that probably wasn't appropriate. It was one that was already in the stack that gets used for 205. It probably wasn't appropriate there. And then the last one was, I think so far only one person has submitted um, stuff related to the projects. And again, I want to be real. I actually am going to resist putting a real rubric up for the simple reason that don't show that again. For the simple reason that I want to be generous, and if I put a rubric up, I feel like I might have to be less generous than I would otherwise. So basically, what I want to do is 25 points come for documenting some sort of a project, and I'd like to see three things there. One is basically whatever you hand your students that you might end up doing for the project. So basically, project handout of whatever that is, the description, and it does it, and if you can tie it to state standards or anything like that, there's already one example up that does some of that. That's fantastic. That's not required. Whatever you might give your students, and if it's derivative from the ASM stuff, that's fine. Um, Secondly, would be a couple examples of student work. And whatever form that takes is fine, and to scan that and turn it into PDF is my preferred way to take it, but if it's easier to put it in the mail or anything like that, I'm okay with it. And then the third thing I would really like is your reaction as a teacher. Basically, I think this part worked. I think this could have been better. Here's what I'd like to do in the future. And then in the end, what I'd also like to do, and is if you could even give this up front, is an okay to publish. And then somehow through ASM Foundation or through our own website, we might put that up somehow and basically use that as a basis so other teachers can extend this material. And I think what we're hoping to do is over time develop sort of an ethic where high school material science or K-12 material science is not something that's necessarily controlled by a for-profit publisher, but as a collective effort of professionals who look over the content and make sure that it's the right sorts of things are being taught, and then the teaching experts, people like you that deal with the students who actually know how to deploy it and craft this in a way that it engages their students, which is something that I might have some ideas on, but I'm usually more wrong than right there. So anyway, those are the things I'd like to do for any of the projects, and basically uh, projects. My pen stopped working. It's not a good sign. But each of these projects, what I was hoping to say is each of these projects is 25 points each, and I'm trying to, if anything, make things a little easier. I want everybody to do a little something here, and everybody to get good grades, and I recognize everybody is busy with other things, so not kill yourselves on it, hopefully also. So today, what I want to talk about is polymers and how they're, first of all, different from metals and ceramics. And you're not really deep in metals and ceramics, but I think enough to understand metals and ceramics typically have crystal structures. And they have metals and ceramics usually have ionic, metallic in the case of metals, or covalent bonding, very strong bonding. And polymers have a mix of covalent bonding and secondary van der Waals bonding. That really changes things. As a result of that kind of bonding, entropy turns out to be something that's really important. It drives the structure, drives a lot of the behavior as well. And these materials are largely amorphous, not crystalline, and that's something we can figure out by X-ray diffraction. Secondly, the mechanical properties are strongly dependent on temperature, and polymers don't really melt, so that we're not really going to worry about a melting temperature. So not TM. Instead, we're going to be worried about TG, which is a glass transition temperature. And I'll bring this up again at the end, but one way you can see TG is if you look closely at how an ice cube forms, you have a very clear difference between solid and liquid. Candle wax is different. There isn't a real clear boundary of solid and liquid. There's some that's harder than others, and there's a temperature range over which properties change pretty quickly, but it's a continuous change in properties. It's not this is solid, this is liquid, and then they have their properties. You can kind of have something where it gets softer and softer and softer, and then turns to something that is like solid to like liquid, and it's not the same sort of phase transformation, and that's basically the sort of thing that a glass transition temperature is about. We'll see that put out directly in graphs and quantitatively soon also. And the other thing about polymers is they're really cheap and easy forming processes. And as a result of that, we can take materials that are fairly cheap on a per pound basis, processes that are cheap and easy to make shapes out of them. And the natural result of that is we have oceans full of Happy Meal toys and things like that. And that's sort of good and bad. It basically is a cheap way to make lots of stuff that we need. It's also a cheap way of making lots of stuff we don't really need, and that can sometimes be a problem. But from an engineering point of view, I think that's mostly a good thing, that there are ways of making plastics into shape very easily, and we'll talk about that, and injection molding being the primary one. Okay, what I want to do now is introduce what polymers are. I think you kind of understand this, but one of these is, for example, polyethylene. Polyethylene, based on the ethylene C2H4, and normally that's two carbons that are double bonded together with hydrogens that sit out here. That's your ethylene molecule. What you can do is you can split this double bond and hook this up to other carbons like this, and make long, almost infinitely long chains like this. And if you take those ethylenes, make a lot of them in a chain, we call that polyethylene. And there's a degree of polymerization, which means how many of these mers are part of that. Typically, with polymers, we're talking on the order of 100,000 to 1,000,000 of these mers in that, and that's what gives you a high polymer. That's what gives you a polymer with high density sort of polyethylene material. So that's polyethylene, and these are all covalent bonds that you see in that picture, and that's how you get that. Polyvinyl chlorine, polyvinyl chloride is similar, except you've got these chloride groups that are part of the chain. Polypropylene, you see here again, just changing the groups to these bulky side groups on here. And all of these things change the properties. These are all materials as we see them here that are called thermoplastics. We'll define that in a moment. And Again, you can understand a lot of what goes on with respect to the structure based on the chemistry, the chemical bonding. And by chemical bonding, we get this zigzagged 109-degree angle between the carbon backbone. But you can imagine that around each of these, there's a lot of degrees of freedom. These can twist like tinker toys, so there's no reason these are straight. And I think certainly all of you who are chemistry teachers know about the two big forces of nature, one being enthalpy, which is going, this nature wants to go to a low energy state, and the other being entropy, that means nature wants to go to a disordered state. As you go higher and higher in temperature, entropy tends to dominate over enthalpy. And so these things are almost never straight. Instead, they wrap up and back around themselves, and they get into these long, complicated, tangled shapes. The other thing that happens is there's a slight positive charge on the hydrogens, a slight negative charge on the carbon backbones. As a result of this, you get basically hydrogen bonding, secondary bonding between the chains, much weaker bonds than the covalent bonds that act between them. And so these long, complicated chains also tend to stick together, and with a bond that's much, much weaker. So this gives you some really interesting properties, and you can actually understand a whole lot about polymers through the structure properties of just knowing that there's covalent bonds along the chains, secondary bonds that stick them together. The covalent bonds do not go away except at very, very high temperatures. But these secondary bonds, like most secondary bonds, this isn't so different than what happens at water. Water evaporates at 100 degrees C. Most of these polymers become noticeably very, very soft, also around the same temperature, around 100 degrees C, and we'll see that quantitatively as we go through this lecture. So again, this is what I was talking about before. Each of these 109-degree angles can take on varied configurations. The material doesn't really care. These chain rotations give you these random kinks, and you get these tangled chains. And it turns out that the length of the chain from end to end, or this, I guess they call it R here, R tends to scale is square root of n, and you can show that a number of ways. There's actually some great math you can put into that. If you just do a random walk problem called the drunkard's walk, you get that, and this would be sort of the drunkard's walk, where he just stumbles each step some random direction. You get that square root of n dependence. Okay, so you've got the covalent bonds along the backbone of the chains, and then inter-chain bonding, you've got secondary bonds between them. And then you can also possibly have covalent bonds by going between chains. So these are linear chains. You could have branches that are on them. These will help entangle, but you see there are not bonds between the branches. And then you can also have chains that are cross-linked, where you see that these are now stuck together. So you can imagine what happens if you take a structure like this that's cross-linked, you heat it up, basically there's very little attraction between these chains, but they're stuck together. Just as a bit of foreshadowing, a cross-linked polymer above its glass transition temperature is what we call an elastomer. It's like a rubber band, so you could imagine when you pull on it, you can stretch this thing, and because the chains don't hold on to each other very much, then you let go, they strap back because they want to maximize their entropy. They want to maximize their disorder. They want to see these chains tangle up like that. And then you can get network polymers like this, where again you get higher and higher degrees of covalent bonding, and you can see as you generally go from this side of the map to this side of the map, you're getting stiffer and stronger And stiffness, remember, back is a resistance to reversible deformation. Strength is a resistance to permanent deformation. They're fundamentally different things, and don't worry if this doesn't come clear to you. Most of our undergraduates, it takes, a lot of them don't get it by the time they graduate. It's a point we repeatedly hammer. But stiffness is resistance to elastic deformation. Strength is resistance to permanent deformation. These will primarily get stiffer as you end up going along. So as you see more and more covalent bonding, you see strength go up. You also see ductility, the amount they can stretch before breaking, decrease. Okay, and you can kind of see again the theme of material science running all through this. What we are doing here is we're relating the structure, which depends on how these bonds form, how they go between each other, to the properties of the material in the end, and that's the heart of this scientific discipline. The other things that matter are the molecular weight, that is the degree of polymerization, the number of the repeat links in the chain. This is a small molecular weight. This is a much larger molecular weight. Higher strength, higher stiffness, higher property polymers generally have higher molecular weights. Tensile strength increases with molecular weight because the chains are more entangled. You're relying more on the covalent bonding versus the secondary bonding. So they're harder to untangle, they're harder to slide, and that causes strength to go up fairly significantly. The other thing that can happen is these chains, again, they can kind of fold back and forth on one another, so that if you've seen how water forms, you can get the hydrogens to kind of nestle in with the oxygen. You can see the same thing where the hydrogens nestle up with the carbon, and you can form these regions like this that are fairly crystalline. It's not crystalline quite like a metal, but or a ceramic, but it's close. And that's where these things back up, and then you might see out here where they aren't able to tangle, but then other regions where they're more crystalline. And you can get these structures like this. These are sometimes called spherulites, because these are kind of spherical regions that have fairly high crystallinity and some order within that. And crystallinity is basically the percent crystallinity as a measure of the percentage of the material that's ordered. Annealing, if you take a material that's just injection molded, annealing will tend to cause the amount of crystallinity to increase. That will cause stiffness and strength generally to increase. And so tensile strength and stiffness tend to increase with crystallinity. So again, you can kind of take a polymer and heat treat it a little bit, put a little bit of temperature into it. It allows the chains to have a little bit of mobility, and they can nestle into shape and form these more crystalline structures, give you some additional strength. So temperature plays a strong role. As I said, the primary thing that goes on is as temperature goes up, you don't mess with the secondary bonds very much. They maintain very good strength throughout, but the secondary bonds can decrease in strength quite a bit. So we talked about this before with glasses. This is again the specific volume, inverse of density. You've got temperature on this axis. And for most materials, you go from a liquid down to a solid, and you see a reduction in volume. If you make ice is one that's anomalous. The other way, you see a change in volume. Most metals reduce in volume. If you get something that's just a glass, you'll see it. You'll pass by that. You won't see any change in specific volume at the melting temperature. But instead, what you see is you hit this glass transition temperature. You see a transition from liquid to glass, and that's a glass transition temperature. This is a semi-crystalline material. You see that at you see that just happening partially. And there's a big difference between what goes on above and below these glass transition temperatures. So above this glass transition temperature, the material is actually quite pliable. Below the glass transition temperature, basically there's not enough free volume for the polymer chains to move past one another, and the material becomes much more rigid. So what we can do is we can plot out properties as a function of temperature and molecular weight for a given plastic at a given temperature. And you see a remarkable, and you've all seen this with plastics, you can see some that are stiff and brittle, some that feel leathery, pleather, plastic leather, in a wide range of properties that can be very appealing from a design point of view sometimes. So as molecular weight goes up, you tend to see things that are generally more uh, uh, generally more crystalline, although this graph doesn't. And then I'm not going to comment on. You can see crystallinity at both sides. I actually believe as weight goes up, crystallinity tends to go up also. As temperature goes up, if you get above the glass transition temperature, certainly above the melting temperature, you do not see crystalline materials as much anymore. Basically, by definition, you get above the melting temperature, crystals won't persist anymore. But you can get these tough plastics here that are somewhat pliable through here, like Tygon tubes you've played with are above the glass transition temperature, but well below the melting temperature. I believe a Tygon tube is a thermosetting plastic, meaning that it has cross links between the chains. Here you see rubber. This is where you have a cross-linked material that is above its glass transition temperature. Here you've got like candle wax, low molecular weight, high temperature, and you get this wide range of properties. Okay, so one thing I don't think I defined very carefully yet, but should as one of the key things here, is when you get back to this point of view over here, if you've got materials where there's only secondary bonds holding the chains together, as you see in this case, these are what we call, I'll change color for emphasis, these are what we call thermoplastics. Meaning that we can heat them up, turn them into a liquid, or something that's like a liquid, and melt them and resolidify them many times. That's like a thermoplastic. Candles are that way. Candle waxes are low molecular weight plastics, basically. They're all hydrocarbons, very similar. These are what we call thermosets, meaning that once we form these bonds, we can heat them up. They will soften with temperature, but they won't really melt. They'll just burn. Okay, and epoxy is an example of a thermoset. Rubber is an example of a thermoset. The vulcanization of rubber, it basically means the cross-linking of rubber. That's a process that was developed by Charles Goodyear, and that was commercialized first in Akron, Ohio. And Akron, Ohio remains today really the center of the rubber, of the thermosetting plastic industry. Really, that's the heart of polymer science, is really in Akron, even today. And it's amazing the way these clusters persist, but a little bit of an Ohio point of pride there too. And those of you watching kind of what's going on in Ohio, we're also getting big discoveries of high-grade hydrocarbons with respect to Marcellus shale. And that actually means possibly some very interesting things for our already very strong polymer industry here, which is kind of neat. Polymers are primarily amorphous. They have lots of defects. You can have deformation resulting from kinked chains and stretching. Chain ends can be chemically different. That can be very useful if you're making paints, adhesives, other functional surfaces, liquid crystals. So you can do some really interesting things by basically putting functional ends onto a surface and then attaching different things to the back, and you can make multi-layers and all kinds of interesting things. Lots of interesting material science related to this, particularly related to soft materials and making biologically active materials. Again, it's all about defects. It's all about different parts of the chain having different kinds of properties. So again, we can classify polymers, and a lot of it has to do with how heating affects structures. Again, I already gave you the basic definition of thermoplastics and thermosets. Thermoplastics are things you can melt and resolidify, and so long as you don't damage the chain weight too much, you can reuse polymers quite a bit. Turns out that you do end up damaging the chain weight as you go take them through the processing we'll talk about. So you can't keep reusing them as much as you would like, as much as, for example, you might be able to with aluminum, where you could remelt and resolidify and it doesn't change. With plastics, the chain weight does tend to degrade with time and working. But thermoplastics are ductile. There's little, if any, cross-linking. They're reversibly softened with heating. Examples are polyethylene tetraphthalate, polyethylene PVC, PET, for example, is what your Coke bottles, your plastic ones are made out of. Polyethylene is typically what milk jugs are made out of. Very easy to process these things. Thermosets are usually more hard and brittle. You can do things with them like Corvette bodies, which are things like fiberglass, glass fiber mixed with epoxy. There's a lot of cross-linking. They don't soften with heating. They can be better structural materials. There's actually some, the reason thermosets are used so often generally more has to do with they're easier to process into shapes like this. There's some really interesting things going on with high property fibers such as graphite and glass and so forth with thermoplastics in it. Mixing those with thermosets is often easier. But examples of thermosets are polyester resins, epoxies, phenolic resins, which go into surface boards, and elastomers, vulcanized rubber, as I talked about before, the material that made Akron famous. So that's those classifications again. So in terms of tensile response, again, you can see this as a structure that changes properties. If you start with a fairly crystalline polymer, these can be kind of disoriented. Here's the amorphous regions, and as you go through, you see a peak in the load. You can form a neck, and this neck elongates, and these necked regions are areas where the material is very highly aligned, and where the material is very highly aligned, you actually see improved properties because your covalent bonds are all lined up in the tensile direction. As a result of that, you see extremely high stiffness and extremely high strength along the tensile direction of that polymer. This is also fairly high entropy, or fairly low entropy situation where everything is stretched the same way. Nature would rather see things random. So very often if you take this and heat it back up, you'll see it suck back close to its original shape, not exactly. And that's one of the experiments we often do in these materials camps is show the shrinky dink effect, where if we heat a polymer, we can cause it to change its shape, go back to this high entropy shape that is low energy that it really likes. This is a kind of experiment you can do very easily with a milk jug, or even these things that are used to hold 6-packs together. That's also polyethylene. You can cut out a little piece of that, and if you pull on it, you can even do this by hand. You'll see exactly this kind of crazing, and you'll also see the optical properties change in this region, and that's precisely because the material is becoming highly oriented, and you can even see it get kind of more milky, and it's actually you're getting some deformation-induced crystallinity that goes on there. It's interesting stuff. The other thing that you will often see in thermoplastics, particularly the more brittle ones like polymethyl methacrylate and polystyrene, is you'll see crazing. Sometimes you can see this even happening just by the stresses that exist in the bottom of a cup as it goes through the washing machine. A lot of times, you'll see some crazes form, and you see these little cracks that are bridged by these little fibrillar bridges, and these might still even be able to hold water, and that's a crazing sort of failure. So we can use this to deform material by drawing, and we can use this as a method to improve its strength. And just as a bit of an example of this, polyethylene, the same material that we use to make milk jugs, it's a very low property material most of the time, but exactly chemically the same material is called Dyneema or Spectra. It's not made by drawing, but it's formed directly in a very highly aligned state. And Dyneema and Spectra are the go-to materials for bulletproof vests. And basically what we do is we just take the fibers and align the polymer chains very well along that direction. It gives us very, very high strength, very, very high stiffness. And if you make a mat of this material and a bullet tries to get through it, it basically can't because those fibers are so strong. Turns out that hardened bullets, like steel bullets, can get through it fairly easily. So for military grade stuff, we use ceramic in front of this. But if you have a lead bullet, it'll spread out the lead bullet and cause it to stop. So anyway, drawing, and that's sort of the process we did by stretching. It stretches the polymer prior to use. It aligns the chains, increases the elastic modulus, increases its tensile strength. It turns out decreasing the ductility. And then if you take that and anneal the material afterwards, which means heat it up just above its glass transition temperature, start giving those chains a lot of mobility, what you'll see is the alignment being decreased, and you'll see the effects of drawing being reversed, causing that to shrink, giving you what I sometimes call the shrinky dink effect. And shrinky dink is a great toy you could even use to teach this form of science. And if you look on the web, there's actually a fair bit on how entropy works into all of this. And that's a fairly advanced topic, but I think an interesting one. Thermosets tend to be less, you can't stretch them generally as far, with the exception of elastomers, and it depends a little bit on how densely cross-linked they are. And the density of cross-linking is something that can be controlled chemically. That controls basically the stiffness and hardness, or durometer, as people like to call it in the plastics business of the plastics. So if you've got something that is fairly highly cross-linked like this, will fail fairly brittly. If something is not as densely cross-linked, you can see the same sort of thing, but again, typically not the same kind of elongation you'll see in a thermoplastic polymer. And again, if you were to take this material, stop the test here, heat it back up again, it will probably shrink back down for you. So an elastomer is basically something that's fairly lightly cross-linked, and it exists above the glass transition temperature. And again, we can chemically control what the glass transition temperature is. So if you've got something that's heavily cross-linked, you might see brittle failure. Moderately cross-linked here, lightly cross-linked above glass transition temperature, you get an elastomer. Again, you get huge strains out of this. The trains can uncoil, but they don't slide. And if you release it, again, it has to be above glass transition temperature. It'll go back to the high entropy or low energy configuration. And temperature and strain rate work separately. If you go to higher temperature, it's easier for chains to slide past one another. If you just go more slowly, there's also more time, makes it easier for chains to slide past each other. This is semicrystalline polymer polymethyl methacrylate plexiglass. And so you can see that this is high temperature, or also very low strain rate. As temperature decreases, chain mobility goes down. You're going from above TG here to below TG. And you see that that's causing the material to get much stiffer, much stronger. Elongation goes down dramatically. Again, if you take this material and you heat it up again, you can do the shrinky dink effect on it. Polymethyl methacrylate works nicely with that. So remember, in metals, we defined a Young's modulus or sometimes called modulus of elasticity. Which is basically a change in stress divided by a change in strain. Well, in polymers, what happens is if you leave a load on something, it'll generally keep creeping. It doesn't just stretch and stop. It'll usually keep stretching and stretching and stretching. So we use something called the relaxation modulus, which is basically hold the strain fixed, measure the stress at a given time, then you get a relaxation modulus based on that. And what we can do is plot that relaxation modulus as a function of function of temperature over here, and for a given polymer, and we see if the temperature is very low, the modulus is very high, and it turns out, and again you notice this is a log scale, so between here and here, this is a factor of what? Factor of 10 to the 6, or a factor of 1,000,000. So you're having something this would be 1,000,000 times stiffer here than down here, 1,000,000 times more higher stress at the same strain. So big changes are indicated on this diagram. So what you see is at low temperature it's fairly stiff, and then all of a sudden you've seen from here to here a factor of 100 change, from here to here another factor of 10 change, or another factor of 100 change from there to there. And this is a glass transition temperature where things change very rapidly. So you go from something up here that's glassy, something that's more leathery, to rubbery, to at this temperature it's liquid. And again, that's what you'd see if you just kind of melted a milk bottle or something like that. So at really low temperatures, it could feel almost like a piece of window glass. Get it to a high enough temperature, and it's like hot honey. And that's pretty much for similar sorts of reasons. Breaking the second, basically what you're doing is you're being able to just break those secondary bonds thermally very easily, is basically what's going on. So we can use these properties. So the thing that's really neat, though, is you get to this region here, you've got a liquid that is a kind of a thick liquid. It's a viscous liquid, again, kind of like honey. And it's actually pretty easy to process that material if you do it right. That's what I was talking about at the beginning. It's easy to make shapes out of plastic. We've got forming techniques. Common one is injection molding. Basically what we do is we've got this feed hopper full of little pellets, typically is the way the plastic comes in. You put them into basically a big screw here and a ram. You get the material plastic, no void, no air bubbles in it. Then just the ram comes through and fills it into a mold cavity. All of a sudden, there you go. You got a happy meal toy in every mold cavity. Easy thing to do. If you're making long shapes, you can do extrusion. Basically, again, just use sort of a screw here. Just have the material come out, and you can make long, complicated extruded shapes with that. With thermosetting materials, we often use something called compression molding. Just basically heat this up. We can make a composite this way with fiberglass in it, squeeze it down, let it cure, pull it out, got a shape. If you make a bottle, we can do blow molding. What you basically do is use injection molding first to make this shape called a parison. And the cool thing about plastics at high temperature is they will behave almost like chewing gum. Result of that, you can put gas pressure inside of it, go blow this out, and make this bottle shape. And then cool it off, and boom, you got a Coke bottle or whatever kind of bottle you like. And again, because you've gone from here to here, you've stretched those plastic chains in directions that reduce their entropy. Material likes to be high entropy, so if you end up going back and heating that up with a hairdryer, it'll tend to go back, not exactly, but tend to go back towards that parison shape, and that's that shrinky-dink effect that I keep talking about. Well, that's basically it. So here are possible experiments you can do in your classroom. I mentioned shrinky-dinks. Another one you could do, I don't think this one was written up in the ASM handbook so much, is elastomer elasticity. You actually find out that if you heat elastomers up, they become stiffer, and that's because entropy basically is a more important driving force as temperature goes up. And be happy to call me. I can talk somebody through that. You can also demonstrate glass transition temperatures. You can see that as you go, if you take something like Tygon tube, bring it to liquid nitrogen temperatures, it will become very brittle. You can break it up. It's because you've gone from above to below the glass transition temperature. You can look at the solidification of the melting behavior of wax or a polymer versus water. A favorite demonstration of mine along these lines is you can see that there's not a real strong difference. There's a continuous difference between solid and liquid as you go through that glass transition, but there are big changes between them. My favorite demo is you take a milk jug, doesn't look like a milk jug, and pretend there's a cap there, and you can take a hair dryer to it, and this is part of the ASM demo. Take sort of a region and concentrate on that. Take it till it goes from milky color to clear. You've got to basically where the material has become more or less liquid there. It still is hanging around. It won't go anywhere. If you blow quickly in the top, you can make this big, nice bubble, which shows how easily the material can be processed, basically, and you get this great polyethylene film there. So you can see how temperature causes these materials to change. You can also go into how it's made sorts of videos and do some of these things in your classroom. Work with thermosets, thermoplastic, foam plastics, and there are distinctly different processing methods used for thermoplastic thermosets. You can also do things with slime and gels and hydrophilic and hydrophobic plastics, and there's actually a fair bit in the ASM series on that, but that's not something I chose to talk about today. Okay, that's it for plastics. One more summary slide. So polymers have some nice advantages. They're lightweight, easily formable, good electrical insulators, usually pretty chemically inert. They don't corrode typically. They do have some problems with environmental stability where they can crack over time. There are mechanical advantages to them. There are disadvantages. First, strength, stiffness, toughness, application temperatures are fairly small. They will often creep on you over time. They're hard to use for real structural things. As a result of that, we typically have to reinforce them for more structural applications, hence fiberglass we like a lot. Thermoplastics tend to be tougher, tend to have smaller things like modulus and strength. Fairly easy to form. They're pretty good in recycling. I think aluminum and steel make much better recycling materials. Aluminum and steel you can reuse really infinitely. You can keep that loop going sustainably pretty much forever. Polymers don't quite work that way. The chain lengths degrade and you really have a hard time renewing that. That's a problem. So there are some ways of being more sustainable with them, but you can't recycle them infinitely. Thermosets are very hard to recycle. They generally have higher strength and stiffness, usually not as tough. KC is fracture toughness, by the way. I don't think I've really introduced that before. And then elastomers have these very, very special properties like you make in car tires and rubber bands, really neat materials. Okay, that ends the polymer lecture. What I want to do is do two quick things. Talk a little bit about phase diagrams and talk a little bit about a corrosion question that was in the last lab, and I'll be fairly brief about these. And hopefully that this helps. So what I want to do is go back to the phase diagram thing. This addresses a couple comments on the discussion board. Remember, there's three things you can get out of phase diagram. One, number of phases. Two, the composition of each phase. And third is the amount of each. I took a picture, a micrograph. This is aluminum 12% silicon by weight. And this comes from this really nice website out of Cambridge, England. And what you see here is most of the structure, this is eutectic solidification here. This eutectic solidification are basically, this is silicon over here, and then the lighter colored stuff in between, this is all aluminum. Okay, so you see most of this all in here is all eutectic solidification. You also see these other regions here. These are basically aluminum. And that's the structure that we will get every time when we let this kind of alloy solidify. So what I want to do is ask the question, just above, if you have something that's aluminum 12% silicon, just above the eutectic temperature, let's say about 580 degrees C, what's the amount of number of phases we have, the composition of each phase, the amount of each phase, and can we back that up with this? So if we do that, I'm sitting just here, just shy of this eutectic point, would be about 12%, and 580 degrees C sits just above this line. So with that, this is liquid plus silicon, this is alpha silicon plus liquid. This phase field here is liquid plus alpha. So I've got two phases here. What's the composition of each phase? Well, this tells me that the alpha has about 1.6% silicon in it. And then the silicon is nearly pure. You've dissolved very little aluminum in the silicon. So the composition of each phase is you've got aluminum plus 1.65% silicon, and then you've got relatively pure silicon. And then how much of each phase is the last question. And we see that you're pretty close to eutectic, and so it's going to be mostly eutectic, and there'll be a little bit of primary aluminum. Well, this is this primary aluminum, this stuff here. And if I do the math on the top of this, ask the question, how much primary silicon should there be? It should be this distance. It should be 12.6 minus 12 divided by 1 point, divided by 1 point, sorry, 12.6 minus 1.65, and when you do the math on that, it turns out to be about 6% aluminum. And this looks like a little bit more than 6% primary aluminum, but it's not, it's in the right ballpark. That looks like about 10%, so the composition might be a little bit off. And that's our lever rule. So basically the lever rule says the amount of alpha is this distance divided by that distance. Okay, that distance divided by that distance. Okay, hopefully that helps. I tell you, this does take a while to sink in, even if you do a lot of quantitative problems. But it is useful. It is accessible a little bit. The other one in the corrosion section, there was a question asked: what happens if you couple nickel and Inconel? And Inconel really isn't defined. Inconel is nickel basically plus aluminum, and the aluminum gives it a little bit better corrosion resistance yet. And the answer that is correct, and this comes from Jerry Frankel, and I just used the questions he used with that lecture, and wasn't thrilled with that question, is he said really nothing should happen. And the idea is that the Inconel and Inconel doesn't show up on here, but you see some, well, nickel aluminum bronze isn't, but you see these nickel alloys sit very close to one another on this galvanic series, which means that they should be fairly compatible. So for marine service, you see this is in voltage up here. This is corrosion potential in salt water, and basically typically we say if two materials are within 150 millivolts of each other, they're not going to corrode very badly. That probably isn't in the lecture. What is in the lecture is there are two reactions. There's an anode reaction of the type nickel goes to nickel 2 plus 2 electrons, and that reaction can go on in some regions, and that'll go in the more anodic side. So materials of these type tend to run that anode reaction very easily. And then you've got other places that can run the cathode reaction. That very common kind of cathode reaction. So you have water around and it's aerated, and you add electrons that could come from here, and they're easily conducted, and that can go to and create hydroxyl groups and make the water more basic. So anyway, the point is, if these are very different, they will tend to do that. The answer that's in that set that I think is a kind of a tricky problem is it really shouldn't corrode too much after all. Okay, we're almost at the end. Please hand in projects at your convenience. I have to look at my calendar to tell you again what day I'm hoping to have, but we are trying to get the class more or less wrapped up by the 16th, so I can have grades in by the 19th. I will add everything up pretty soon, and again, good grades require some combination of lectures, which if you're listening to this now, you're clearly doing that, and the project. And again, project can be fairly free form. Please get hold of me any way you like, and we can make sure that everything gets done and in on time. That's it for now, and we'll be talking more, I'm sure. Thanks. Bye.